It wasn't. Okay. I've still got that stupid green box. Okay, so we're going to talk about a lot of different types of diodes. Zeners, varactors, pin diodes, which I never knew what a pin diode was. I thought it was something with a pointy contact or something, but that's not what it is. Schottky's, actual point contacts, and LEDs. So diodes are two-terminal devices. They have what we call an anode and a cathode. They conduct current in only one direction up to a point, because in the case of a Zener diode, it will conduct in the reverse direction when you get it up to the Zener voltage. So they've taken a basic diode and do different manipulations with it to create all these different types, whether it's a varactor diode or a Zener diode or a Schottky diode. It's just the way they're constructed. And some manipulation of the actual semiconductor material. They may not use the same type of doping that would you see in a transistor, particularly for light emitting diodes, where they use some, no, I can't remember what they are, some various compounds that work better as far as emitting light, especially at different light colors or frequencies. A simple diode we represent with this triangle and a bar, representing the anode and the cathode. In most cases, the actual device will be marked with a stripe on the cathode end.
Excuse me a second, that's gallium arsenide for the LEDs.
Say that again?
Gallium arsenide for the LEDs.
Gallium arsenide phosphate, actually.
Yeah, well, whatever.
And then it's surrounded with some other material that enhances it. The Zener diode is like a normal diode with the cathode represented more like a Z. A Schottky diode is kind of a swastika diode. Its basic difference is it has a lower threshold voltage. The varactor diode we show with the capacitor symbol on the cathode because we're going to use it as a voltage controlled capacitor. Hopefully I don't talk about a lot about tunnel diodes because I don't really understand them, but we represent it with that. I guess that's kind of to represent a tunnel. It has to do more with the quantum physics stuff of how electrons get to one side or the other of the junction. If it's a light emitting diode, we show these little arrows representing the light being generated from the diode. It turns out all diodes generate light. The p-n junction, as the electrons recombine, they release energy. And that energy can be in the form of light. It depends on the amount of energy, and that determines the frequency. So they just learn how to enhance that effect. In most cases, the diode is in a package where it doesn't let the light out, whereas in a light emitting diode, it's in a clear package or a colored package. And then you have a photodiode that's the opposite, where it allows light to come into the p-n junction and actually create a potential. And that's true for any diode also. If you were to expose the p-n junction, it would be affected by light. They do the same thing with a phototransistor, where they put a little clear lens where light can get onto the base emitter junction of it and create that voltage potential. We talked earlier about the P-type and N-type, and then the I-type, which is called intrinsic silicon or pure silicon. So when we dope it, then we classify it as a P or an N, depending on whether we wind up with free electrons or holes. We did this before, we talked about the p-n junction. So when we do a Zener diode, it actually allows current to flow in both directions. In the forward bias or normal mode, it acts like a regular diode. And it will pass current at, if it's a silicon, which most of them are, at the 0.6, 0.7 volts. If you reverse bias it, it will pass current when you get to what's called the Zener voltage, or it's a reverse breakdown voltage. And then it appears to have almost zero resistance. And we can use that as a voltage reference or even a voltage regulator, where it'll try to maintain that constant breakdown voltage. This is just a plot showing when you forward bias it, when you get up here to the knee, it starts to conduct. And the slope of that line is going to be a function of the internal resistance of the diode plus whatever external resistance, because it's going to have a little bit, so it's not a perfectly vertical line. When you reverse bias it, you actually get some leakage current up to the point where you get this knee effect and it avalanches or Zeners, because it was named after some guy, I think, named Zener. And maintains a fairly constant voltage at that point. So what's the most useful characteristic of a Zener diode? Yeah, they didn't make it easy the way they worded the answers. There's a couple key words there, though.
I've never heard of current drops. I think that's kind of maybe what threw A out of there.
Okay, so you're going to throw out A. It's not a varactor, right? So, and
I'll take B.
you're going to take B. We have a Bravo, a Bravo, lots of Bravos. Bravo wins. You can have a varying current. The current's not a factor as long as you're exceeding the Zener voltage. It'll conduct current in reverse direction. Varactor diodes, like I mentioned before, they make use of the fact when it's reverse biased, the bias potential affects the width of the depletion zone, and therefore the capacitance between the two terminals. So it's a voltage controlled variable capacitor. And in fact, in most modern stuff, you don't see mechanically or mechanical variable capacitors hardly at all. They'll be varactors. They're a whole lot cheaper. If anybody has priced any old-fashioned variable capacitors, they're like gold. The way they construct them is slightly different than the others. You have the p-n junction where you have an enhanced N down here, which has got excessive N doping with the regular N, and the metal contact on the top, which I think these things are set up so it enhances the depletion zone effect. So you can have a larger change in capacitance than you would on a normal diode. But you can use a normal diode in reverse and get some variable capacity. So what type of semiconductor device is designed for use as a voltage controlled capacitor? That was kind of easy, wasn't it? Some of them are easy. A pin diode. It's called pin because it's a P type, an I type, and an N type. So it actually has a layer of pure silicon between the junctions. And its main claim to fame is it can be used as a variable resistor at high frequencies, a voltage controlled variable resistor. So you don't have to have a pop to physically turn, you can do it electrically. And it's constructed with those three layers, like I said. The symbol has the line going all the way through. So it's slightly different than your normal diode signal. So what characteristic of a pin diode makes it useful as an RF switch? Charlie. Yeah, I don't like any of the answers, but Charlie is
No, it's not right.
is not right. I don't think I mentioned on the other one, but because of the way it's made, it has a lower capacitance, which is why it's useful at RF frequencies, because that's the big problem when you start getting high frequencies. The capacitive effect, parasitic and internal, is what limits what frequency you can operate devices at. But it's normally used as at high frequencies as a switch to like select bandpass filters. So you can have a bunch of filters separate with pin diodes and bias those remotely and select whichever bandpass filter you want. And that's how most of the modern radios are done, as opposed to actually using some small high frequency relays. What is used to control the attenuation of RF signals by a PIN diode?
Okay. Oh,
Well, let's see. Alpha. Okay, Schottky diodes. Another one named after an old German. They sometimes call it a hot carrier diode, although I don't hear that much anymore. But it's basically a junction between metal and semiconductor material. And it gives you a much lower voltage drop than you would with a silicon or germanium. It also, I think, has a little lower capacitance, so it can switch very fast because of the lower capacitance and also the lower voltage. So they use it a lot in high frequency mixers or envelope detectors because of the voltage drop and the fact that it can operate at much higher frequencies. It's made with some metal. I don't know whether they use gold or exactly what, and some N-type silicon. And you have this very small junction there, which I guess is representing the depletion zone. So it's going to be very small. So it's going to have a small amount of capacitance. And the symbol is this, I call it the swastika, but it's only half. If you look at actual cross section, you can see where you've got the N-type layer, the silicon oxide, which is an insulator. And then I guess in this case, well, they just say metal. And they're using gold wires. If you actually take one apart, and a lot of these devices will actually, like the integrated circuits, will actually be connected with very, very small gold wires out to the pins. So what characteristic of a Schottky diode makes it a better choice than a silicon diode for use as a power supply rectifier?
D.
Lower forward voltage drop, which gives you lower headroom than a normal voltage regulator. One of the problems is how much, if you want a 12-volt supply or output, how much voltage do you have to put in order to maintain 12 volts out? And it's usually a 2 or 3 volts because of the devices used. Which of the following is a common use of a Schottky diode? Low capacitance, what's that do for you?
You said it can be used as a VHF, UHF detector, so I say D. I've heard you use the word mixer, so yeah, once you said the same thing.
Well, we didn't talk about mixers yet. Usually, a lot of mixers are made with an array of 4 diodes in a ring. Which of the following is a Schottky barrier diode? What's different about the Schottky from the others?
A,
Yep.
Okay. Point contact diode. I think this is kind of the old gallium crystal that used for crystal radio, where you have a cat whisker making contact with it, and you have this little PN junction. Because of the way it's made, it has a very low junction capacitance, and they're normally germanium, because germanium tends to have a higher carrier mobility than silicon does. I guess that means there's more free electrons per mass than silicon. I'm not exactly sure. And you usually find these in things like an RF detector, another high frequency device, low current. It's not a power device. What's a common use for point contact diodes?
Crazy.
Sounds like Charlie. Light emitting diodes. We use them all the time now. There's hardly anything that doesn't have a light emitting diode. We're even changing out fluorescent lights with them. One of the problems is most of the cheap Chinese controllers generate a tremendous amount of noise. And as an amateur, you will find that out. But when you forward bias an LED, just like a normal diode, you can have current that flows. Because of the fact that it's made from different material, the band gap is different and the threshold bias voltage is different. It's usually up in the volt range, 2 or 3, 3.5 volts, depending on the diode. And it's somewhat affected by the color that they want to produce. And we talked about the schematic. So when it's flowing current, it is releasing energy in the form of photons at a certain frequency. And the frequency is going to be proportional to the amount of energy that the electron has when it was freed from its atom and then recombines and it releases that energy back. It's still a normal p-n junction, but like I said, it's made out of different material. And the band gap is much larger. So it typically has a higher threshold voltage. So it's going to release more energy. And they've learned how to control the size of the gap and the material itself. They surround it with some other material that the light from the light emitting diode kind of causes, like in the old cathode ray tube, causes the phosphorescence of the material, so it enhances the light and the color. So they can make just about any color you want. You can find them in all kinds of shades. And that color will be proportional to the size of that band gap, the amount of energy that's being released. So what property of an LED semiconductor material determines its forward voltage drop?
B.
Yeah, you just said band gap.
Yeah.
Somebody listen.
That's too easy.
That was too easy?
Yeah.
A lot of them are easy.
Hey. Wait for that.
We did the hard ones first.
We did.
Yes. Okay, which of these is the symbol for a Schottky diode?
Oh,
Let's see. Number 6. Junction temperature. That's one of the things you have to watch for semiconductor devices. When the temperature of the junction, and it goes up depending on how much current is flowing through it. At a certain temperature, it will fail. And one of the things about silicon devices and all the semiconductors made out of them is, since silicon isn't really a metal, it behaves differently than a metal. If you increase the current through a metal conductor, the resistance goes up. Okay, and it heats up because you got more resistance. In the case of a silicon device, it's just the opposite. The resistance decreases as the temperature goes up. When you have a device like that in the circuit, you can have what's called thermal runaway, where as the current's increasing, the resistance is decreasing. What's that cause? More current, more heat. And then you have one of these devices where the smoke got left out. So what causes the junction diode to fail from excessive current? B. Excessive junction temperature. Let's see.
So did we actually finish?
No. Did I forget to record that?
No, you got up there, second from the top, it says pause or stop recording.
Oh, it's up there.
No, in your dialogue box there.
Oh, I didn't see it. Okay.